case of projectile motion is when you have zero launch height. Zero launch height meaning that your projectile is fired or thrown or kicked or whatever from the same height that it lands at. And there are a lot of properties of zero launch height that make it useful. We can just go ahead and use our normal projectile equations. So x is still v naught x times t, and we can say that our y final equals y naught plus v naught y t minus 4.9 t squared, but in the case of zero launch height, our y naught and y final are both 0 because we're at ground height. So then we just have 0 equals v naught y t minus 4.9 t squared. And we can apply those equations, and we will apply those equations, in addition to using the acceleration equation from time to time. But it's also useful to exploit some of the qualitative properties of this motion. Now this is a lot like what we talked about in 1D, where an object goes straight up and then falls straight back down. At the peak here, if it goes straight up and straight down, the velocity is 0. Here, the overall velocity is not 0. However, at the peak, the y velocity is 0. It's still moving horizontally, but in the vertical direction, it's stopped for an instant in time. Okay? So we can use that. We can also use the symmetry of this motion. So this is symmetric, just as this was. The speed right here is the same as the speed right here, except in this case it was going up, whereas over here it's going down. If you're with points here and here, the speeds here and here are the same. Sorry, and here, the speeds here and here are the same. In this case it's going up, in this case it's going down. Right? And that is true of this too. So this v naught and v final are very similar. The magnitudes of those two are the same, because we already know that our x velocity is constant throughout the whole motion. Well, our y velocity, here it's going up, and over here it's going down with the same magnitude. So the magnitudes of the initial and final velocities are the same. And these two angles are the same. So with theta naught and theta final are the same, our initial angle is going to be above the horizontal, and our final angle will be below the horizontal. So we can apply these equations, but there are also these symmetries we can exploit. One more thing, we know that this peak happens halfway through the motion. All right? So we know that the distance, x distance at the peak, is half the x final, the total distance, and we know the time at the peak is half the time it takes to hit the ground. Oh gosh, that does not look like a half. 1/2 t final. That's better, a little bit. Sorry about that. All right, so we can use these two to solve various problems. So let's say I wanted to find, let's say we have a ball is kicked at 15 meters per second at 22 degrees above the horizontal. And I want to know how high does it go? What is its highest point? Well, its highest point, of course, is at this peak. And we know at this peak that the y velocity is 0. So we can exploit that to figure out how high the ball goes, because we can just use our time-independent equation. 2ay delta y equals vy final squared minus v naught y squared. We know that our acceleration in the y direction is minus 9.8. Delta y is what we're trying to figure out. Our final velocity in the y direction is 0. That's the key feature we're exploiting. And our v naught y, we know, is v naught sine theta. And if we plug that all in, we can figure out that delta y comes out to about 1.61 meters. So that is how high it goes. All right. Let's say we want to know how long it takes to get there. Now we can do that using just our definition of acceleration. Acceleration is delta v over t. Our acceleration in the y direction is minus 9.8. Our final velocity in the y direction is 0. Our initial velocity in the y direction is 15 sine 22. And so we can figure out that our time is about 0.573, etc. All right. Now let's say I ask, how far away does the ball land? Okay. Now we could do the same thing that we did when we were just applying the kinematic equations. We could solve the y equation, plug in 0 here, solve for time, and plug that into the x equation. But using what we've already found, we can exploit the properties of this motion, because we know this time to peak is half the total time. So we know the total time is just that 0.573 times 2, which is about 1.146. And then we can plug that time into the x equation, and that's just v naught x, 22 times time. And if we plug that in, we get that the distance it travels is about 17.2 meters. Right? What if I want to know what is the final velocity of the ball as it hits the ground? Well, again, we could go through the process we did here, where we calculated the final velocity in the y direction and its magnitude and direction and all that. But we can exploit the symmetry. We know the final velocity is the same as the initial velocity, or the magnitude is the same. We know the angle is the same, but the final velocity is just below the horizontal, where the initial velocity was above the horizontal. So again, we can do calculations and whatnot when we have 0 launch height, and that's fine. But we can exploit these symmetries to make some of our questions easier to answer.